Okay, so we left off talking about molecular geometry. And molecular geometry is based off of something called VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. So if you think about, if you have electrons that are in a bond, electrons are negatively charged, or whether they're in a lone pair, electrons have like charges, so they're going to repel each other, right? So it says to determine molecular geometry, we can start with a steric number. So remember, to review for the fourth time, if you have a single bond, that counts as a steric number of 1. Two bond or double bond is a steric number of 1. Triple bond counts for 1. A lone pair counts for 1, and an unpaired electron, they all count for 1. So if you look at this molecule, the carbon has 4 single bonds, so its steric number is equal to 4. Okay. Now, if we look at ammonia, NH3, it's got 1 lone pair and 3 bonds. So again, its steric number is 4. And then if you look at water, or the central atom, the oxygen, has 2 bonds and 2 lone pairs. So they all have the same steric number. Do these 3 molecules have the same molecular geometries? No, not at all, because molecular geometry only considers bonds. Okay. So now, when it comes to hybridization, we can look at the steric number. If the steric number is 4, it's sp3. If the steric number is 3, it's sp2. If the steric number is 2, it's sp. So that means that the carbon and nitrogen and oxygen in all 3 of these molecules, respectively, they're all sp3. This is sp3, the nitrogen is sp3, and this oxygen, they are all sp3 because they all have the same steric number. But to repeat myself, do they have the same molecular geometry? The answer is no, because molecular geometry only considers bonds. Do they all have the same number of bonds? No. The carbon has 4, the nitrogen has 3, and the oxygen has 2. So if we have 4 bonds, then we have a tetrahedral molecular geometry, tetrahedral. If we have 3 bonds, then we have 3 bonds, 1 lone pair. We have trigonal, pyramidal. And if we have 2 bonds and 2 lone pairs, then our molecular geometry is bent. I repeat, molecular geometry only considers bonds. Now, why would you consider all these tetrahedral? You would say they don't have a tetrahedral molecular geometry, all of them. They have a tetrahedral electron group geometry. So we say they all have a steric number of 4. Okay, so they all have the same electron geometry. So to repeat, okay, molecular geometry considers only what? Bonds. Electron geometry considers bonds and lone pairs. Okay, molecular geometry considers what? Only what? Bonds. Is a lone pair a bond? No, it is not a bond. Electron geometry considers bonds and lone pairs. So if you look at all 3 of these, they all have a tetrahedral electron geometry. Why? Because methane has 1, 2, 3, 4 bonds. That means it's got a tetrahedral electron geometry. Ammonia has 1, 2, 3 bonds and 1 lone pair. 3 plus 1 is 4. It's got a tetrahedral electron geometry. And the oxygen in water has 2 bonds, 2 lone pairs. Electron geometry considers bonds and lone pairs both. So these all have a tetrahedral electron geometry. Do they have the same molecular geometry? No, because the carbon here has 2 bonds. The nitrogen here has 3 bonds. And the oxygen here has 2 bonds. And this is why they all have different molecular geometries. The carbon in methane, CH4, has 4 bonds. Therefore, it's tetrahedral. So if you're saying, well, that means that this molecule has the same molecular geometry and the same electron geometry. Yes, it does. If you look at ammonia, NH3, okay, its electron geometry is tetrahedral, but its molecular geometry only considers the bonds. So it's trigonal pyramidal. And then in water, okay, the oxygen in water, yes, it's got 2 bonds and 2 lone pairs, but it's bent, okay? Why? Because we only consider the bonds. It's got two bonds. Give me a thumbs up if you see the difference between molecular geometry and electron geometry. Sometimes they are the same, yes. If there's no lone pairs on the central atom, yes, they are the same. But if there's lone pairs, they are not the same. All right. So now that we've got that straightened out, what are the molecular geometries that you need to know? If we have a steric number of 4, so we'll start with these. All three of these have a steric number of 4. There's 3 possibilities. You can have 4 bonds and no lone pairs. You can have 3 bonds, so 4 bonds and no lone pairs. You can have 3 bonds and 1 lone pair. You can have 2 bonds and 2 lone pairs. These are the 3 examples that are shown on this slide, 3 examples shown on this slide, 3 examples shown on this slide, okay? All those are what we've been talking about for the past 5 minutes. Now, what if you have 3 bonds and no lone pairs, like in boron trifluoride? So that would look something like this. In this case, the boron has no lone pairs on it, and so the molecular geometry that's going to be adopted in this case is going to be trigonal planar. It's going to be flat, and you're going to have a bond angle of 120 degrees. And then if you have something like beryllium hydride, okay, so you have BeH2, like this, it's got 2 bonds, no lone pairs on the beryllium. So your bond angle is going to be 180 degrees, and your molecular geometry is going to be linear, because it's straight. Now keep in mind that when you have no lone pairs on the central atom, that the molecular geometry and the electron geometry are identical. The only time they differ is when you have lone pairs on the central atom. So what's the summary? If you have a steric number of 4, you've got 3 possibilities. If there's no lone pairs, it's tetrahedral, your molecular geometry. If there's 1 lone pair, it's trigonal pyramidal. And if there's 2 lone pairs, it's bent. The examples that we used were CH4, NH3, and H2O. If you have a steric number of 3, if you have 1 lone pair, it's going to be bent. An example of that would be something like sulfur dioxide, SO2. You can take the time to make that Lewis structure, or boron trifluoride, if it's got 3 bonds and no lone pairs. And then linear, the example that he used in the book was beryllium hydride, BeH2. All right, so there you go. So now you see the relationship between steric number, hybridization, electron geometry, and molecular geometry. They're all summarized on this slide. So now that we have that in our brain, let's see if we can use Vesper theory to predict the geometry for each of the following structures. So I've got BH4 minus this compound here. This is called borohydride. The name isn't important, but could anybody tell me what would the molecular geometry for this be? You got a boron with 4 single bonds. What is the molecular geometry for this boron? It's tetrahedral. Thanks, Aaron. Absolutely, right? You've got the boron with 1, 2 bonds that are going to be in the plane. I'll draw 1 bond in the back and 1 coming out in front like that. Okay, put the negative charge. Our bond angle is going to be 109.5 degrees. All right, now what about the BF3? What's our molecular geometry here? 3 bonds, no lone pairs. It must be trigonal planar. I love it. Right? Don't even have to do anything to this one. We'll just put here trigonal planar. Okay, and in both of these cases, you could say that in both of these, the molecular geometry is equal to the electron geometry in both of them. Why? Because there's no lone pairs on the central atom. Just one aside before we move on. In chemistry, whenever somebody says predict the geometry and they don't give any word before it, they always mean the molecular geometry. It always means molecular. Okay, but if they specifically say what is the electron geometry or the arrangement of electron pairs or something, that means they're talking about electron geometry. All right, there you go. Why don't we call it a day, since we covered a lot of content. And what we'll do in tomorrow morning's class is we're going to cover section 1.11. So we'll cover dipoles. Then we're going to cover intermolecular forces. So we're going to talk about dipole-dipole forces, hydrogen bonding, and London forces. Then once we're done that, there's just a very, very short section at the end where it discusses, where is it here? Solubility. So we'll talk about solubility in the axiom like dissolves like. So polar compounds dissolve polar compounds, nonpolar dissolve nonpolar. And then we'll talk about soap, and then we'll be done. Okay, so we'll finish that tomorrow morning, and then we'll get into chapter 2. And just to remind you, oops, not the syllabus, I wanted the schedule. Chapter 2 is molecular representation. So we'll start talking about things like bond line structures and all that good stuff. Remember, since the Wiley link doesn't seem to be working, I did post a version of the textbook in the chapter 1 module that you can take a look at, and the solutions manual is posted there as well. So you have free reign over that. And again, I'll contact the publisher and I'll get that working as soon as possible. But you have more than enough practice problems to get going, and all the content is covered in that textbook. What does that sound? Must be my